Welcome to the Deep Sleep Science Channel. Tonight we'll rest our attention on time in space, how motion, gravity, and distance gently reshape what a moment means from one place to another. Before you get too comfortable, you're welcome to like, subscribe, or leave a quiet comment to support the channel, and then let your thoughts slow as we begin. In special relativity, the time measured by a clock traveling along its own path, its proper time can be less than the time measured by a clock considered at rest in a chosen inertial frame. The difference is described by the Lorentz factor, which depends on the traveler's speed compared with the speed of light. As the speed gets closer to light speed, the factor grows, and the separation between your time and their time becomes more noticeable. This is not a trick of the clock's gears or electronics, but a difference built into the geometry of space-time. Time dilation is not a physical fatigue of a mechanism, as if a moving clock simply struggles to tick. Instead, it reflects that two observers following different world lines between events can accumulate different amounts of elapsed time. In relativity, time is part of the interval that joins events in space-time, and that interval depends on the path taken. So, slower time is really a different measure of the same separation, not a local breakdown of physics. Proper time is the most intimate kind of time in relativity. It is what an ideal clock measures while it simply accompanies an object. It does not require choosing a global coordinate grid, and it does not depend on how distant observers label slices of now. It is the time that a person, a particle, or an instrument would actually experience along its journey. This makes proper time the natural language for describing aging, onboard mission timing, and local physical processes. Two observers in steady relative motion can each say the other's moving clock is running slow, and this can be true without contradiction. The reason is that comparing distant clocks requires a rule for simultaneity, what counts as at the same time, and that rule changes with the observer's motion. So each observer's comparison uses a different set of simultaneous moments. The situation feels strange only if you assume a single universal present that everyone shares. Relativity of simultaneity means that two events judged simultaneous in one inertial frame are generally not simultaneous in another frame moving relative to the first. This is not about measurement error. It is a structural feature of how space and time fit together. When you change frames, the tilt of now changes, reshaping which distant events line up together. That is why the statement "they happened at the same time" can be true in one frame and false in another. In general relativity, gravity influences time so that clocks deeper in a gravitational potential tick more slowly compared with clocks higher up, even par, when both are at rest relative to the source of gravity. The effect is subtle near Earth, but becomes dramatic near compact objects like neutron stars and black holes. It is not that gravity directly pulls on time, but that gravity is space-time curvature, and curvature changes how time is measured along different paths. This is why altitude and gravitational environment matter for precision timing. In weak gravitational fields, gravitational time dilation can be described as a fractional difference in clock rate that scales with the potential different star. Divided by Lito 1/4fx 2c2. This makes the effect small in everyday life because Lito 1/450 is enormous, but it becomes measurable with modern atomics 18. Clocks. The same relationship also connects directly to gravitational redshift, linking clock rates to the color and frequency of light escaping a gravity well. It is a gentle reminder that timekeeping is sensitive to where you are in the universe. Velocity time dilation and gravitational time dilation can either compete or cooperate, depending on the situation. Moving fast tends to reduce elapsed proper time relative to a chosen rest frame, while being higher in a gravitational potential tends to make a clock run faster relative to one deeper down. In orbit, both effects appear together, and the net result depends on the orbit's altitude and speed. Practical systems must treat both contributions carefully rather than assuming they cancel. For many low Earth orbits, the speed of the spacecraft produces a slowing of onboard clock rate relative to ground clocks, while the slightly weaker gravity at Tau altitude produces a small speed-up. Whether the net effect is a small loss or gain of time depends on the exact orbital parameters. Even when the difference is tiny, it accumulates steadily, and precision timing systems notice it. Spaceflight is one of the clearest everyday environments where relativity becomes operational. Astronauts on the International Space Station age a little bit less than people on the ground over the same span of coordinated time, because they're orbital Brissi. Speed introduces measurable kinematic time dilation. The difference is extremely small on human timescales, but it is real and calculable. It is not a special property of the station. Any fast-moving, stable orbit would show the same pattern. What makes it striking is that the effect is part of ordinary life in orbit. The twin paradox is resolved by recognizing that the traveling twin changes inertial frames, typically by accelerating to turn around or change course. The symmetry between twins is broken because only one follows a single inertial frame the whole time. In space-time language, the twins follow different world lines between the same departure and reunion events. The result is that one world line can contain less proper time than the other. From the space-time viewpoint, the twin who experiences acceleration often follows a path that accumulates smaller proper time between departure and return than the twin who remains approximately inertial. The difference is not a moral lesson about acceleration. It is a geometric fact about paths in spacetime. Even if acceleration happens quickly, the overall world line can still differ in a way that changes total elapsed time. Proper time depends on the whole journey, not just on what happens at a single moment. The speed of light, letter 1d450, acts as a conversion factor that ties distances and durations together in a single space-time interval. This is why relativity often treats time in units where letter 1d4 affix O equals 1c equals 1, making time and space appear as different directions in the same structure. In that view, a time difference can be related to a distance through the geometry of the interval. It is one reason light plays such a central role in defining what can influence what. Light travels along null paths in spacetime, and along such a path, the proper time is 0. This motivates the common statement that a photon does not experience the passage of time, though it is important that a photon does not have a standard inertial rest frame in which it can be treated like an ordinary observer. Still, the mathematics captures something clear. The interval along light's trajectory is different from that along any massive object's world line. In the geometry of spacetime, light sits at a special boundary. Coordinate time is a time label assigned by a chosen coordinate system, useful for bookkeeping and prediction, but not necessarily equal to any single berbra. Physical clock everywhere. Different coordinate choices can slice spacetime in different ways, assigning different time coordinates to the same events. This is especially important in curved spacetime, where no global coordinate choice is uniquely preferred. Good physics keeps track of what is coordinate-dependent and what is invariant. In curved spacetime, there is generally no single universal now that all observers can share as a global slice of simultaneity. Local observers can define a present in their immediate neighborhood, but extending it across large distances becomes frame and geometry dependent. This is one reason cosmology and strong gravity astrophysics rely on carefully defined reference frames and timescales. The universe does not hand us one privileged clock that everyone must agree on. As gravity strengthens near a compact object like a neutron star, differences in clock rates between nearby regions can become large. A clock on the surface of a neutron star would tick noticeably more slowly relative to a faraway clock than a clock on Earth would. This is a direct consequence of strong curvature in spacetime. It also influences how emitted radiation is observed, because the timing and frequency of signals carry the imprint of gravitational redshift. Near a black hole, gravitational time dilation relative to faraway observers becomes extreme. Signals emitted closer and closer to the event horizon arrive increasingly delayed and increasingly redshifted, so their energy and cadence fade from view at a distance. This can make processes near the horizon appear slowed and dimmed from the outside. Yet locally, near the infilling object, the laws of physics can remain ordinary in a small region. An event horizon is not a physical material surface. It is a boundary in spacetime that marks where escape to infinity becomes impossible for light. The horizon is defined by causal structure, not by something you could touch. Crossing it is about which future paths remain available, not about striking a wall. This is why the horizon is often described as a feature of spacetime itself. For a distant observer, infilling matter can appear to approach the event horizon ever more slowly, largely because of gravitational redshift and the way light signals are stretched and delayed. The outside observer receives signals that become weaker and take longer to arrive, creating the impression of an endless approach. This is not because the infailing object freezes in its own experience, but because communication becomes increasingly suppressed. The view from far away is shaped by signal propagation in curved spacetime. For the infilling observer, crossing the event horizon can occur in finite proper time, without any special local marker that time has stopped. In idealized conditions, the local environment near the crossing can be unremarkable over small distances because equivalence principles make free fall locally inertial. What changes is not local ticking, but the global ability to send signals back out. The horizon is dramatic in causal consequences even when local physics feels calm. The Schwarzschild solution describes the spacetime outside a non-rotating, uncharged spherical mass, and it predicts both gravitational time dilation, the bending of light. He provides one of the simplest exact models of a black hole's exterior. In this geometry, the relationship between time at different radii can be computed cleanly. It also shows how what looks like gravity can be expressed as spacetime curvature. The Kerr solution extends this to rotating black holes, introducing effects that do not appear in the non-rotating case. Rotation changes the geometry so that spacetime itself is dragged around, altering the motion of particles and the behavior of clocks in orbit. The structure of horizons and stable orbits depends on spin. This makes rotation a central ingredient in realistic black hole timing and accretion behavior. Frame dragging is the effect where a rotating mass influences nearby spacetime, causing local inertial frames to twist relative to distant stars. It affects gyroscopes, orbit precession, and the detailed timing of orbits around rapidly rotating objects. In strong gravity, it becomes a dominant feature of the motion. It is one of the clearest ways rotation and time become physically entangled in relativity. In a rotating spacetime, what it means to be at rest becomes less straightforward than in flat space. Local inertial frames are not globally aligned, and the natural notion of non-rotation can vary with position. This affects how clocks compare, how orbits behave, and how observers define their reference directions. Rotation makes the geometry itself carry a kind of built-in motion. In strong gravity, time dilation influences not only clock readings, but the rates of physical processes, because those processes unfold along proper time. A chemical reaction, an atomic transition, or a biological rhythm is governed by local time. So when two regions differ in clock rate, they also differ in the pace at which identical local physics accumulates duration. In that sense, time dilation is not confined to clocks, it is a universal scaling of local evolution. Gravitational redshift is closely tied to gravitational time dilation. Light climbing out of a gravitational potential arrives with a lower frequency than it had when emitted. The photon's frequency shift matches the relative rate difference between clocks at emission and reception. This allows gravitational time effects to be probed by spectroscopy and precise frequency comparisons. It is one of the ways gravity leaves a measurable imprint on light. A clock can be realized in many ways: atomic transitions, stable oscillators, or even the steady spin of pulsars and relativity predicts consistent K. Time dilation across all ideal realizations. The physics does not depend on the clock's mechanism when the clock is ideal and well oscillated. This principle is part of why relativity can be tested using very different technologies and astrophysical systems. The agreement across clock types supports the idea that time dilation is fundamental, not mechanical. Atomic clocks keep time by counting extremely stable frequencies associated with atomic or ionic transitions. Because these transitions are so regular, atomic clocks can detect minute influences, including changes due to motion and gravity. Their precision turns relativity from an abstract theory into an engineering reality. They also serve as reference tools for synchronizing systems that rely on timing down to nanoseconds. The modern definition of the second is tied to a specific hyperfine transition in cesium-133, providing a stable reference that does not depend on Earth's rotation. This decouples basic timekeeping from the subtle irregularities of planetary spin. It also makes timescales more uniform for science and technology. Civil time can then be derived from atomic time while still being kept roughly aligned with the day. Earth's rotation is not perfectly uniform, varying due to tidal friction, shifting winds, ocean dynamics, and movements within Earth's interior. These variations are small moment to moment, yet they matter over months, years, and decades. They are part of the reason that astronomical time and atomic time slowly drift apart. Earth's day is a living, changing rhythm rather than a perfect metronome. Because Earth's rotation is irregular, a timescale tied directly to Earth's rotation, such as UT1, gradually drifts relative to atomic timescales. UT1 captures the true orientation of Earth relative to the Sun and stars, but it does not tick uniformly. Atomic time, by contrast, is designed to be as steady as possible. The difference between the two must be monitored and published for precision applications. Coordinated universal time is kept close to UT1 by occasionally inserting leap seconds, so civil clocks remain aligned with the Sun's daily paras. Pattern within an agreed tolerance. Leap seconds are not scheduled on a fixed cadence because the drift rate varies. This creates a timekeeping compromise, steady atomic seconds, with occasional adjustments to stay near Earth rotation time. It is a reminder that time in daily life is both physics and convention. Leap seconds can be disruptive for computer systems and networks because not all software handles an extra second in the same way. Some systems repeat a second, some smear the adjustment across a window, and others risk glitches if assumptions about monotonic time are violated. This makes leap seconds an engineering challenge even though the adjustment is tiny. In a world of high-speed transactions and synchronized infrastructure, a single second can be surprisingly complicated. Terrestrial time is a theoretical smooth timescale tied to clocks on Earth's geoid, widely used for astronomical calculations. It provides a clean reference rate, avoiding irregularities in Earth rotation. By defining a standard context for Earth-based proper time, it supports consistent modeling of planetary motion and observations. It is one of several carefully defined scales that make precision astronomy possible. International Atomic Time is a continuous timescale produced by combining data from many atomic clocks around the world. Using an ensemble improves stability because independent noise sources average down. TAI provides a backbone for modern timing, even though most daily life references UTC. In practice, TAI is a global effort. Many laboratories contribute to a shared measure of steady time. GPS time is a continuous timescale used by the Global Positioning System, related by defined offsets to other standards like TAI, UTC. Unlike UTC, GPS time does not incorporate leap seconds in the same way, which keeps it continuous and convenient for engineering. Receivers account for the offsets when they need civil time. This separation between continuous system time and adjusted civil time is common in navigation systems. Satellite navigation depends critically on precise time because positioning is fundamentally a measurement of signal travel time. The receiver estimates how long a signal took to arrive, converting that time into a distance by multiplying by the speed of light. With enough satellites, those distances intersect to give position. In this sense, navigation is timekeeping turned into geometry. In GPS, a timing error of 1 nanosecond corresponds to roughly 30 centimeters of range error, because radio waves move about that far in a nanosecond. This illustrates how time precision translates directly into spatial precision. It also explains why stable clocks and careful corrections are essential. When you ask for your location, you are really asking for a time solution. GPS satellites experience both gravitational and velocity time dilation relative to clocks on Earth, creating a net offset that must be corrected. If those corrections were ignored, satellite clocks would drift relative to system time in a way that rapidly corrupts position estimates. Relativity is therefore built into the system's design rather than applied as an afterthought. Navigation works at global scale partly because time is modeled with relativistic care. Without relativistic corrections, GPS position solutions would drift, and errors could grow quickly to levels that would overwhelm everyday navigation. The reason is that even small clock rate mismatches integrate into large time offsets, and large time offsets become large distance errors. In timing systems, steady bias is more dangerous than random noise because it accumulates. GPS shows how theoretical physics becomes practical necessity. GPS receivers solve for their own clock bias along with position, which is why signals from at least 4 satellites are typically used for a full 318 dimensional fix and time solution. The receiver's internal clock does not need to be perfectly accurate. It needs to be stable enough to assist the solution. The system uses redundancy and geometry to estimate the unknown timing offset. In this way, positioning and timekeeping are solved together. The Sidemak effect appears in rotating reference frames and causes signals traveling in opposite directions around a rotating platform to take different travel times. Earth's rotation makes this relevant for global systems because the ground and the coordinate frame attached to Earth are not inertial. When signals cross long distances, Earth turns during their flight. Correcting for that rotation is part of making global timing consistent. Earth's rotation produces a Sidemak correction in GNSS because signals traveling through Earth-fixed coordinates experience the frame's rotation during DAPRA. Propagation. Even though the signal flight time is only a fraction of a second, Earth rotates enough that the correction matters for precision. The effect becomes a predictable term in navigation equations. It is another example of how motion and time intertwine. In deep space navigation, Two-way light time is the round-trip travel time of a radio signal sent from Earth to a spacecraft and returned. This round trip can be minutes or hours depending on distance, and it sets the pace of tracking and command confirmation. Two-way ranging benefits from using the same ground reference clock for both transmission and reception. It turns time delay into a measurable ruler across the solar system. Radio signal travel time to distant spacecraft makes real-time control impossible in the familiar sense, placing a premium on autonomy and careful Bora. Planning. Commands arrive later, and confirmation arrives later still, because the return signal must also cross the distance. This forces mission teams to think in predicted timelines rather than instant feedback. In deep space, patience is not just a style, it is part of physics. Light time delay is not only a communications inconvenience, it is also how distances and spacecraft states are inferred. Tracking uses time-tagged signals, and the finite speed of light becomes the bridge between what is sent, what is received, and where the spacecraft must have been. This turns timing into navigation. In a very literal way, the spacecraft's story is written in delayed light. The Shapiro time delay is a relativistic increase in signal travel time when a signal passes through curved space-time near a massive object like the Sun. Even if the path length in ordinary geometry seems similar, space-time curvature adds extra delay. Measuring this delay has served as a test of general relativity and as a practical correction in precise tracking. Gravity, here, appears not as a pull on objects, but as a stretch in the timing of light. In astrophysics, looking out into space is also looking back in time, because light takes time to travel. A distant galaxy is seen not as it is now in Earth's frame, but as it was when the light began its journey. The farther you look, the deeper into cosmic history you observe. Distance becomes a kind of archive of earlier eras. The cosmic microwave background is observed as it was when the universe became transparent, providing a snapshot from very early cosmic time. It carries information about conditions in a hot, dense era, long before stars formed. Because its light has traveled for so long, it arrives with wavelengths stretched by cosmic expansion. In the sky, it is one of the clearest examples of time preserved in radiation. Gravitational lensing can produce multiple images of a background object, and those images can arrive at Earth at different times. The delays occur because each light path has a different geometric length and passes through different gravitational potentials. Time delay measurements help infer the lens's mass distribution and can inform cosmological modeling. Here, gravity shapes not only where light goes, but when it arrives. In deep space navigation, time is the central quantity from which distance and motion are inferred. Engineers do not directly measure how far a spacecraft is by stretching a ruler across space. Instead, they measure how long it takes a signal to travel. That measured duration is then translated into distance using the known speed of light. Over interplanetary scales, even small uncertainties in timing can translate into vast uncertainties in position, making time the quiet backbone of exploration. Two-way ranging is especially powerful because it uses a single ground-based time reference to mark both the transmission and reception of a signal. The spacecraft simply reflects or retransmits the signal, allowing mission controllers to compute distance without needing the spacecraft to maintain an ultra-precise independent clock. This method reduces sensitivity to onboard clock drift and ties navigation directly to Earth-based atomic time. Over millions of kilometers, this shared timing reference becomes a stabilizing anchor. One-way ranging becomes possible when a spacecraft carries a clock stable enough to timestamp its transmissions accurately. In that case, Earth does not need to wait for a return signal to estimate distance. It can compare the transmit time encoded in the signal with the receive time on the bow. Ground. This approach allows more autonomy and can reduce tracking demands, but it places far greater importance on the spacecraft's onboard timekeeping. The balance between autonomy and dependence on Earth is, in part, a balance between clocks. Highly stable onboard clocks open the door to navigation architectures where spacecraft operate with less constant oversight. With reliable timekeeping, a spacecraft can plan maneuvers, coordinate observations, and even collaborate with other spacecraft based on shared time references. This shifts mission design from continuous ground control toward predictive, time-driven operations. In deep space, time becomes a tool for independence. Deep space tracking also relies heavily on Doppler measurements, which examine how the frequency of a received signal shifts due to relative motion. Because frequency is directly related to time cycles per second, Doppler tracking is another way of reading motion through timing. A steady change in frequency reveals acceleration, while stable offsets reveal velocity. Together with ranging, Doppler data paints a dynamic picture of a spacecraft's journey. Coherent Doppler tracking uses transponders that lock the outgoing signal to the incoming one, preserving phase relationships across the round trip. This coherence allows extremely precise velocity measurements, sensitive to tiny accelerations. Over time, these measurements reveal gravitational influences, thrust events, and subtle forces. Once again, timing and phase stability are the quiet enablers of insight. The Deep Space Network maintains widely separated antenna complexes around Earth to provide near-continuous coverage as the planet rotates. Time coordination between these sites is essential because data from different stations must align within strict tolerances. Earth's rotation, motion around the Sun, and orientation changes all feed into timing models. Even ground infrastructure must think cosmically about time. As Earth rotates, different tracking stations take over communication, requiring seamless handoff in time-tagged data. Each station's clock, location, and motion must be precisely known so that signals can be interpreted consistently. This means that deep space timekeeping is not just about space, it is equally about Earth as a moving platform. The planet itself is part of the timing system. Light time delay shapes mission operations because commands sent to a spacecraft arrive long after they are issued. Mission planners must think ahead, scheduling actions based on predicted future states rather than immediate feedback. Confirmation of success arrives even later, reinforcing the need for confidence in timing models. Space missions operate not in the present moment, but in carefully forecasted futures. Because of this delay, autonomy becomes essential for handling unexpected events. Spacecraft are programmed with fault protection systems that respond immediately to anomalies without waiting for Earth. These systems rely on onboard clocks to sequence actions correctly. When something goes wrong far from Earth, timekeeping ensures the spacecraft can act calmly and consistently on its own. Precise time standards also underpin radio science experiments, where small changes in signal timing or frequency reveal physical properties of care. Space. Variations in signal delay can indicate gravitational fields, atmospheric density, or plasma conditions. In these experiments, time itself becomes a sensor. The universe leaves fingerprints in how it delays and shifts signals. Gravitational fields add subtle delays to signal propagation beyond simple geometric distance. When a signal passes near a massive object, space-time curvature lengthens the travel time. This Shapiro delay must be modeled to avoid misinterpreting timing data as distance changes. Gravity quietly stretches time along the signal's path. Shapiro delay has been measured within the solar system using radar and spacecraft links, confirming predictions of general relativity. These measurements show that time is not merely counted locally, but is influenced along the entire route a signal travels. The delay depends on how closely the signal passes to the mass and how strong the gravitational field is. Even empty space near a mass carries a temporal cost. In interplanetary communication, modeling Shapiro delay improves navigation accuracy, especially when spacecraft are near superior conjunction with the pole. Sun. During these alignments, signals pass close to the solar gravitational well. Ignoring the extra delay would introduce systematic errors. Precision requires acknowledging that time flows differently along curved paths. Solar plasma also affects signal timing, introducing frequency-dependent delays as radio waves pass through charged particles. These delays vary with solar activity and geometry, adding a time-variable layer to communication. To correct for this, engineers use models or multiple frequencies to estimate plasma effects. The Sun's influence reaches into timing as well as gravity. Very long baseline interferometry measures differences in signal arrival times at widely separated antennas to determine precise angular positions. By comparing when the same wavefront reaches different sites, astronomers reconstruct direction with exquisite accuracy. The technique depends entirely on synchronizing clocks and modeling delays. Time differences across Earth become a cosmic ruler. VLBI timing can locate spacecraft and celestial sources with extremely fine resolution, complementing ranging and Doppler data. It turns Earth itself into a giant interferometer, with time as the glue holding the system together. Small errors in clock synchronization would blur the image. Precision timing sharpens our view of the universe. Earth orientation parameters are required because Earth's rotation axis and speed are not perfectly stable. These variations affect how ground-based time and position relate to inertial space. Timing systems must account for polar motion, nutation, and length of day changes. Earth's subtle wobbles ripple into space-based measurements. The difference between UT1 and UTC is published regularly so users can translate between Earth rotation time and civil atomic time. This information is essential for astronomy, navigation, and satellite operations. Without it, predictions of where Earth-based antennas point in space would drift. Even the sky depends on knowing the time accurately. Precise time distribution on Earth relies on satellite links, fiber networks, and comparison methods that transfer time between distant clocks. Each method must account for signal delays and asymmetries. The goal is not just to keep clocks ticking steadily, but to keep them aligned with one another. Synchrony is as important as stability. Comparing clocks across continents can be limited by atmospheric effects, hardware delays, and path variability. These influences must be measured or calibrated out to reach the highest precision. As clocks improve, the environment around them becomes the limiting factor. Timekeeping pushes attention outward. The stability of a clock is often described in terms of how its frequency varies over different averaging times. Short-term noise and long-term drift affect different applications differently. In space missions, both matter. Short-term stability affects measurements, while long-term stability affects accumulated error. A good clock is calm across many scales. Space is a challenging environment for precision clocks because temperature changes, radiation and vibration can perturb their operation. Designing clocks that remain stable under these conditions requires careful engineering. Shielding, thermal control, and redundancy all play roles. Time must be protected to remain trustworthy. Traption and cold atom clocks achieve high precision by isolating atoms from environmental disturbances. By controlling motion and interactions, these clocks reduce noise and systematic shifts. Their performance reveals how deeply quantum behavior and timekeeping are connected. They represent the frontier of measuring time. Onboard clocks enable one-way Doppler and range observables that reduce reliance on continuous two-way tracking. This can free ground resources and allow spacecraft to operate more flexibly. However, it also shifts responsibility to the spacecraft to maintain its own temporal integrity. Autonomy and trust in time go hand in hand. Spacecraft telemetry relies on accurate time tags so that engineers can reconstruct events after the fact. Every maneuver, measurement, and anomaly is recorded against a clock. Without reliable timestamps, the story of a mission would be scrambled. Time orders experience. Spacecraft often maintain multiple time representations at once, such as onboard event time, Earth reference time, and mission elapsed time. Each serves a different purpose, and conversions between them must be handled carefully. Consistency across these systems prevents confusion. Multiple clocks coexist quietly behind the scenes. Mission elapsed time is especially useful because it runs continuously from a defined starting point, such as launch. It avoids complications from leap seconds or calendar adjustments. This makes it a clean internal timeline for operations and analysis. In the spacecraft's own narrative, elapsed time is the simplest thread. Time correlation files link spacecraft clock readings to Earth-based standards. These correlations are updated regularly to account for drift and offsets. They allow scientists to interpret data accurately long after it is collected. Time, once recorded, must remain interpretable. Spacecraft oscillators age and respond to temperature, causing gradual changes in frequency. Regular calibration keeps these changes from accumulating into large errors. Monitoring clock behavior becomes a routine part of mission operations. Even in space, clocks grow older. Interplanetary missions often use specialized timescales designed for solar system dynamics. These scales simplify equations by embedding relativistic corrections in their definitions. Choosing the right timescale makes modeling smoother and reduces error. Time definitions are tools as much as conventions. Barycentric timescales center the reference frame on the solar system's center of mass, reducing periodic variations caused by Earth's motion. This is especially important for high-precision astronomy and pulsar timing. By stepping back to the barycenter, time becomes steadier. Perspective matters even for clocks. Differences between Earth-centered and barycentric timescales include periodic components tied to Earth's orbit. These variations must be removed to compare signals arriving from distant objects accurately. Timing becomes cleaner when Earth's motion is factored out. Stillness is achieved by understanding motion. Pulsars, especially millisecond pulsars, act as remarkably stable cosmic clocks because of their regular rotation. By timing their pulses, astronomers can track changes over years and decades. These natural clocks extend timekeeping beyond Earth. The galaxy offers its own rhythm. Pulsar timing compares observed pulse arrival times with models that include motion, spin down, and propagation effects. Tiny deviations can reveal new physics or environmental influences. The method relies on long-term consistency and precise timing. Patience turns pulses into knowledge. Pulsar timing arrays combine data from many pulsars to search for correlated timing shifts caused by gravitational waves. These shifts are incredibly small and unfold slowly. Detecting them requires trusting clocks over vast spans of time. The universe whispers through timing correlations. At the particle level, time in relativity is inseparable from motion, because every particle traces a world line through spacetime. Even elementary particles with extremely short lifetimes experience time dilation when they move close to the speed of light. In particle accelerators, unstable particles survive longer than they would at rest, not because their internal physics changes, but because their proper time accumulates more slowly relative to the laboratory frame. This effect is measured routinely and agrees precisely with relativistic predictions. Muon particles created by cosmic rays in Earth's upper atmosphere provide a natural demonstration of relativistic time dilation. Muons have very short lifetimes when measured at rest, yet many reach Earth's surface because they are moving at relativistic speeds. From Earth's frame, their internal clocks run slow, allowing them to persist longer. From the muon's own frame, the distance to Earth is length contracted, shortening the journey. Both descriptions meet consistently in spacetime. Particle lifetime measurements show that time dilation applies universally, not only to clocks built by humans. The decay of particles is governed by the same proper time as any other physical process. This means that time dilation is not an artifact of measurement devices, but a fundamental property of how time is experienced along a path. Nature itself keeps time according to relativistic rules. In experimental physics, frequency standards are often used instead of direct clocks because frequency stability is easier to measure with high precision. Since frequency is cycles per unit time, any shift in frequency reflects a change in time flow. Comparing frequencies between systems in different conditions becomes a comparison of time itself. Experiments translate time into oscillations. Gravitational redshift experiments compare the frequencies of identical clocks placed at different heights in a gravitational field. Even small height differences produce measurable frequency shifts when clocks are precise enough. These experiments confirm that time runs slightly faster at higher altitude. Gravity's influence on time is gentle but persistent. Laboratory tests of gravitational time dilation have been performed over vertical distances of only a few meters. With modern optical clocks, even centimeter-scale height differences can, in principle, be detected through frequency comparison. This brings relativistic time effects into everyday spatial scales. Time becomes sensitive to posture and elevation. Atomic clocks aboard aircraft and rockets have been compared to reference clocks on the ground to measure combined velocity and gravitational time dilation. These experiments show that motion and altitude effects add exactly as predicted. The results match relativity within experimental uncertainty. Even brief journeys leave temporal fingerprints. In orbit, precision clocks experience changing gravitational potential and velocity along their trajectory. Careful modeling allows scientists to predict how clock rates vary over each orbit. Comparing predictions with measurements tests both physics and engineering. Space becomes a laboratory for time. Clock comparison experiments must carefully separate Doppler effects from true gravitational frequency shifts. Relative motion changes observed frequency, so experiments are designed to cancel or measure this contribution independently. Only after removing motion effects can the gravitational influence on time be isolated. Precision requires patience and symmetry. Relativistic frequency shifts also appear in spectroscopy of atoms moving at high speed. The transverse Doppler effect shows that even motion perpendicular to the line of sight leads to time dilation. This confirms that time dilation depends on speed itself, not just motion toward or away from an observer. Time responds to velocity in all directions. In storage rings, ions circulating at relativistic speeds show frequency shifts in their internal transitions. Measuring these shifts tests time dilation with high accuracy. Such experiments rely on controlling electromagnetic fields and particle motion precisely. Time is probed through charged particles in motion. Gravitational time dilation affects not only clocks but also the energy levels of atoms, because energy and frequency are linked. When an atom sits deeper in a gravitational field, its transition frequencies are slightly lower as seen from afar. This connects gravity, time, and quantum mechanics in a measurable way. Fundamental constants appear steady, but their expression depends on space-time context. Quantum mechanics treats time differently from space, often as an external parameter rather than an operator. Yet relativistic effects show that time measured by physical systems depends on motion and gravity. Bridging these views is an ongoing conceptual challenge. Experiments at the intersection of quantum clocks and relativity explore this boundary. Quantum clocks, built from superpositions of atomic states, can, in principle, probe time dilation at the level of single particles. When such a clock is placed in a superposition of heights or velocities, different components experience different proper times. Interference patterns can encode relativistic time differences. Time becomes part of quantum superposition. Experiments with entangled particles require precise timing to compare measurement outcomes. Synchronizing detectors across space ensures correlations are interpreted correctly. Relativistic effects must be considered when distances or motions become large. Even quantum correlations live within spacetime. In space-based quantum communication, timing accuracy determines whether entangled signals can be correlated after traveling long distances. Light time delay, Doppler shifts, and relativistic corrections all influence synchronization. Quantum information depends on classical timekeeping to be interpreted. Time underpins even the most abstract signals. Clock noise, including quantum projection noise and technical noise, limits how precisely time can be measured. Understanding and reducing noise is central to improving clocks. At high precision, fluctuations become the dominant feature rather than systematic drift. Time measurement becomes a study of calmness amid randomness. Optical clocks use transitions at much higher frequencies than microwave clocks, giving them finer resolution per cycle. This allows shorter averaging times to reach a given precision. However, it also makes them more sensitive to environmental disturbances. High-frequency timekeeping requires deep isolation. Comparing optical clocks across long distances demands time transfer methods that preserve phase and frequency stability. Free-space optical links and stabilized fiber links are developed for this purpose. These links themselves must account for motion, gravity, and environmental changes. Time transfer becomes an experiment in control. Space-based optical clocks could compare time rates between orbit and ground with unprecedented precision. Such experiments would test gravitational time dilation more stringently than ever before. They would also explore whether new physics appears at extreme sensitivity. Space extends the reach of precision. Atomic interferometers use matter waves to measure acceleration, rotation, and gravitational gradients. The phase accumulated by atoms depends on the time they spend in different paths. This makes interferometry a timing experiment in disguise. Matter itself becomes a clock. In atom interferometers, proper time differences between paths lead to measurable phase shifts. These shifts can encode relativistic effects, including gravitational time dilation. Experiments exploit this to probe gravity with quantum objects. Time is written into interference fringes. Precision timing also matters in detecting tiny forces, because force-induced accelerations change velocities, and thus Doppler shifts over time. Tracking these shifts reveals subtle influences. Time integrates small effects into observable signals. Patience amplifies sensitivity. Space-based detectors for gravitational waves rely on timing differences in laser beams exchanged over vast distances. Changes in space-time alter the effective path length and timing of light. Measuring these changes requires exquisite stability in clocks and lasers. Time variations become signatures of cosmic events. Laser interferometers measure phase differences that correspond to incredibly small time delays. Even variations far smaller than a nanosecond can be significant. These instruments turn time into a measurable displacement. Space-time ripples announce themselves through timing. In gravitational wave detection, correlating signals across detectors depends on accurate timestamps. Arrival times at different locations constrain source direction. Without precise timing, the sky position would remain uncertain. Time triangulates the universe. The detectors must also distinguish real signals from local disturbances, which requires comparing timing patterns. Noise that is uncorrelated in time across sites can be rejected. Timing coherence becomes a filter for reality. Time helps separate signals from chance. High-energy astrophysics instruments timestamp individual photons to reconstruct variability patterns. The arrival time distribution carries information about source size and dynamics. Shorter variability implies more compact regions. Time reveals structure beyond spatial resolution. Gamma-ray detectors use timing to associate bursts across different instruments and wavelengths. Comparing arrival times helps identify the same event seen by different observatories. Coordinated timing builds a complete picture. Events are woven together by clocks. In pulsar observations, folding data over long times requires precise timekeeping to maintain phase coherence. Even small timing errors can smear the signal. Stable clocks preserve the sharpness of pulsar profiles. Timekeeping sustains periodicity. Correcting pulsar arrival times for Earth's motion involves transforming observed times to a barycentric frame. This removes periodic variations due to Earth's orbit and rotation. Only then can intrinsic pulsar timing be studied. Time must be placed in the right frame to make sense. Dispersion by interstellar plasma delays lower frequency pulses more than higher frequency ones. Measuring and correcting this delay requires accurate timing across frequencies. Changes in dispersion over time reveal plasma dynamics. Time traces invisible matter. The solar wind introduces additional time-variable dispersion that must be modeled in pulsar timing. Its effects change with solar activity and line of sight. Accounting for this improves long-term stability. The Sun leaves temporal fingerprints. Binary pulsars show timing variations due to orbital motion, gravitational redshift, and relativistic effects. Measuring these variations tests gravity and strong field regimes. Timekeeping turns orbital dance into data. Motion becomes readable through delays. Neutron star glitches produce sudden changes in rotation rate that appear as abrupt timing anomalies. Studying how timing recovers afterward probes the star's interior. Time records the star's hidden rearrangements. Sudden moments carry deep information. Timing noise in pulsars reflects irregularities in rotation that are not fully understood. Long-term monitoring helps characterize these variations. Distinguishing noise from new physics requires patience. Time separates trends from fluctuation. In spacecraft tracking, small, non-gravitational forces such as thermal emission can cause tiny accelerations detectable through Doppler timing. These forces accumulate over time into measurable effects. Even heat can leave a timing signature. Time integrates the subtle. Precision orbit determination uses time-tagged measurements to reconstruct trajectories. Errors in timing propagate directly into errors in position and velocity. Maintaining timing accuracy is essential for navigation. Space paths are drawn in time. Atomic clocks on satellites must be shielded from radiation that can cause frequency jumps or long-term drift. Monitoring clock health is a continuous process. Space environments challenge temporal stability. Time needs care. Clock anomalies are logged and analyzed to maintain system integrity. Removing faulty clocks from ensembles prevents corruption of system time. Redundancy protects against temporal failure. Timekeeping is managed like a living system. Time distribution protocols include calibration of hardware delays in antennas and electronics. These delays can be larger than the relativistic effects being measured. Correcting them is essential to see subtle physics. Time measurement demands humility. In experimental relativity, comparing clocks in motion tests the universality of time dilation. Different clock technologies are flown or moved to ensure consistency. Agreement across types reinforces confidence. Time behaves the same, regardless of how it is measured. Precision timing experiments often run for years to accumulate data and average down noise. Long duration is a form of sensitivity. Time reveals itself to those who wait. Duration becomes a tool. In relativistic experiments, the distinction between coordinate time and proper time becomes especially important at high precision. Coordinate time is a convenient label used in calculations, while proper time is what a physical system actually experiences. When experiments compare clocks or signals, they must carefully track which notion of time is being used at each step. Confusing the two can introduce subtle but significant errors. Precision timing experiments often rely on symmetry to cancel unwanted effects. By arranging clocks or particles in mirrored configurations, researchers can isolate the influence of motion or gravity. This approach reduces dependence on imperfect models. Symmetry allows time to speak more clearly. In satellite-based experiments, clocks may be placed in elliptical orbits so their velocity and gravitational potential change predictably over time. As the satellite moves closer to and farther from Earth, its torque rate shifts in a calculable way. Tracking this modulation tests relativistic predictions directly. The orbit becomes a time-varying laboratory. Frequency comparisons between spaceborne and ground-based clocks often involve continuous exchange of signals. These links must be corrected for Doppler shifts, atmospheric delays, and hardware offsets. The remaining frequency difference reveals the relativistic effect of interest. Extracting time requires careful subtraction. Relativistic corrections in satellite systems are often applied as pre-programmed offsets to clock frequencies. By slightly adjusting the clock rate before launch, engineers ensure that the clock runs at the desired rate once in orbit. This proactive correction keeps system time aligned. Time is tuned in advance. Even after pre-correction, residual timing errors can appear due to unmodeled forces or environmental changes. Continuous monitoring allows these errors to be identified and corrected. Timekeeping is not static. It is actively maintained. Vigilance keeps time steady. In laboratory tests, moving clocks at modest speeds can still show measurable time dilation when precision is high enough. Aircraft-based clock comparison experiments demonstrated this decades ago. Modern clocks would detect even smaller effects. As clocks improve, motion that once seemed negligible becomes visible in time. Relativistic effects must be considered in frequency standards used for telecommunications satellites. Stable frequencies depend on stable time, and orbital motion perturbs both. Engineers incorporate relativistic models into system design. Time underlies communication reliability. In metrology, time and frequency standards are compared internationally to maintain consistency. These comparisons reveal not only clock performance, but also relativistic effects due to differing gravitational potentials at each laboratory. Geography becomes part of timekeeping. Earth's shape leaves a temporal imprint. Relativistic geodesy uses differences in clock rates to infer differences in gravitational potential. By comparing ultra-precise clocks at different elevations, researchers can measure height differences. Time becomes a tool for mapping gravity. Clocks double as altimeters. In principle, a clock placed on a mountain ticks faster than one at sea level. With sufficient precision, this difference is directly measurable. This demonstrates that timekeeping can sense the structure of Earth. Time flows differently across landscapes. In space missions, onboard clocks are often synchronized during ground contact and then allowed to free run between updates. The drift during this free run period must be modeled. Understanding how clocks behave in isolation is essential. Time drifts quietly when unattended. Radiation effects can cause sudden frequency shifts in spaceborne clocks, known as single-event upsets. These events must be detected and corrected to prevent lasting error. Space is unpredictable at the smallest scales. Timekeeping must adapt. Redundant clocks on board spacecraft provide resilience against failure. If one clock degrades, another can take over. Combining multiple clocks can also improve stability. Time is safer when shared. Clock ensembles work by averaging the outputs of several clocks. Random fluctuations tend to cancel, while consistent behavior remains. This principle applies both on Earth and in space systems. Collective calm emerges from many voices. In deep space missions, the limited opportunity for ground contact increases reliance on onboard timekeeping. Long gaps between updates make clock stability critical. Errors that would be corrected quickly near Earth can persist far away. Distance magnifies temporal responsibility. Relativistic corrections are embedded in navigation software that predicts spacecraft trajectories. These corrections ensure that time-tagged observations align with physical reality. Without them, predictions would slowly diverge. Time anchors motion. In Doppler tracking, frequency stability over long periods allows detection of extremely small accelerations. These accelerations may arise from gravity, propulsion leaks, or thermal effects. Time integrates these influences into measurable trends. Subtle forces reveal themselves slowly. Thermal radiation emitted by spacecraft can produce a tiny recoil force. Over months or years, this force can cause detectable changes in trajectory. Doppler timing picks up the effect. Even warmth leaves a temporal trace. Timekeeping also matters for attitude determination because sensors record when stars are observed. Accurate timestamps allow reconstruction of spacecraft orientation over time. Pointing history depends on time accuracy. Spacecraft awareness is time-stamped. Star trackers rely on catalogs with precise positions and proper motions. Matching observed stars to catalog entries requires knowing the exact observation time. Timing errors translate into pointing errors. Time aligns the sky. In scanning space observatories, detectors record continuous streams of data. Each sample must be assigned a precise time to map it to a sky location. Time converts motion into images. Without timing, the sky would blur. In cosmic ray detectors, arrival times of particles help reconstruct their trajectories and origins. Coincidence timing between detectors identifies real events. Time separates signal from noise. Particles announce themselves through simultaneity. High-energy particle detectors often use time-of-flight measurements to distinguish particle types. Differences in arrival times across a known distance reveal velocity. Velocity reveals mass and energy. Time decodes identity. Time-of-flight systems must calibrate path lengths and electronic delays precisely. Even small uncertainties affect particle classification. Precision timing sharpens experimental resolution. Time refines discrimination. In neutrino observatories, timing correlations across large detector volumes help identify rare interactions. Synchronizing detectors is essential. Timestamps link faint signals into meaningful events. Time gives coherence to rarity. In astrophysical neutrino detection, comparing arrival times with electromagnetic signals can identify common sources. Differences in timing test propagation models. Time aligns messengers from the cosmos. Multi-messenger astronomy is synchronized. Relativistic effects also influence clocks used in space weather monitoring. Variations in signal timing can indicate plasma disturbances. Timekeeping doubles as environmental sensing. Space leaves marks on clocks. In magnetospheric studies, timing of wave propagation reveals plasma density and field structure. Measuring delays between sensors allows reconstruction of dynamics. Time maps, invisible motion. Rhythm reveals structure. Planetary radio emissions often show periodicities tied to rotation or magnetic field structure. Timing these emissions reveals internal properties. Time deciphers planetary behavior. Cycles speak softly. In planetary atmospheres, wave propagation speeds determine how quickly disturbances travel. Timing measurements help infer temperature and composition. Time tracks motion through air. Even atmospheres have clocks. Precision timing is also essential in inter-satellite ranging systems. Measuring how long signals take to travel between satellites reveals their separation. Formation flying depends on time. Distance is counted in seconds. Laser-based inter-satellite links can achieve extremely high timing precision. Phase measurements encode time differences at sub-nanosecond scales. Light becomes a ruler of time. Precision approaches the fundamentals. Clock synchronization between satellites requires accounting for relative motion and gravitational potential differences. Without correction, clocks would drift apart. Relativity keeps the constellation coherent. Shared time binds the system. In experimental tests of fundamental constants, timing stability ensures that observed changes are real and not instrumental. Long-term clock comparisons can test whether constants vary over time. Time watches itself. Stability becomes evidence. Space missions designed to test relativity often place clocks on trajectories that maximize predicted effects. Careful timing reveals whether reality matches theory. Time is both subject and instrument. Measurement becomes dialogue. In all these experiments, patience is essential. Tiny effects accumulate slowly, requiring long observation periods. Time itself is the resource that makes detection possible. Waiting is part of knowing. As precision improves, experiments probe regimes where different theories might diverge. Any unexpected timing behavior could hint at new physics. Time becomes a frontier. Quiet discrepancies may speak volumes. Through careful design, calibration, and monitoring, experimentalists ensure that clocks remain faithful witnesses. Their steady ticking records the universe's subtle behavior. Time listens while we measure. At extremely high precision, even the electronics used to read clocks introduce measurable delays that must be calibrated. Signal paths through cables, amplifiers, and processors each add tiny offsets. These offsets are stable enough to correct, but only if they are measured patiently. Time measurement includes the entire chain, not just the clock itself. Temperature variations subtly change electronic components and optical paths, affecting timing at fine scales. As environments warm or cool, signal delays can shift. Precision timing systems therefore stabilize temperature or continuously monitor its influence. Time prefers a calm environment. Vibrations, even at microscopic levels, can influence oscillators and optical cavities used in advanced clocks. Mechanical noise couples into frequency, instability if not controlled. Isolation systems are designed to keep clocks still. Silence, mechanically speaking, helps time stay steady. In space, microgravity changes how components settle and age compared to Earth-based laboratories. Some noise sources are reduced while others appear. Studying clock behavior in orbit reveals how gravity itself influences stability. Space offers a different quiet. Radiation-induced defects in materials can gradually alter oscillator properties. These changes occur slowly, over months or years, and must be tracked through long-term timing analysis. Space radiation leaves subtle fingerprints. Timekeeping records cumulative exposure. Single-event radiation hits can cause abrupt jumps in clock phase or frequency. Systems must detect these jumps and either correct them or exclude affected data. Temporal resilience requires awareness. Time must be guarded against surprise. Clock steering algorithms gently adjust clock outputs to maintain alignment with a reference timescale. These adjustments are small and deliberate, avoiding sudden changes. Steering keeps time smooth. Correction is applied with restraint. In large systems, clock ensembles reduce the impact of individual anomalies. If one clock misbehaves, the group remains stable. Ensemble averaging smooths time's expression. Collective agreement steadies the flow. Comparing clocks over long baselines requires correcting relativistic effects due to Earth's rotation and gravity. These corrections are part of everyday precision time transfer. Relativity becomes routine. Timekeeping normalizes space-time physics. Optical fiber links used for time transfer must compensate for path length changes caused by temperature and mechanical stress. Active stabilization systems track and correct these variations. Fibers breathe and time listens. Stability is maintained dynamically. Free space optical time transfer must account for atmospheric turbulence, which causes fluctuations in signal arrival time. Adaptive optics and averaging help reduce this noise. The air itself participates in timing. Time passes through weather. Satellite-based time transfer must model satellite motion accurately to avoid timing bias. Even small orbit errors translate into timing errors. Precise ephemerides support temporal alignment. Motion and time remain inseparable. Relativistic corrections in time transfer are often applied at the picosecond level. At this scale, neglected effects accumulate into measurable discrepancies. Precision reveals completeness. Time rewards thoroughness. In experimental relativity, null results are as important as positive detections. Showing that time behaves exactly as predicted constrains alternative theories. Consistency builds confidence. Silence can confirm the truth. Long-term clock comparisons test whether fundamental constants drift over time. Any slow change would alter clock frequencies relative to one another. So far, stability prevails. Time appears faithful to itself. Particle decay experiments rely on precise timing to measure lifetimes accurately. Statistical distributions of decay times reveal underlying physics. Timestamps become probability maps. Randomness organizes into law. In accelerator experiments, synchronization between particle bunches and detectors is critical. Misalignment in time reduces measurement accuracy. Timing gates observation. Precision opened windows. Time-of-flight detectors distinguish particles by measuring how long they take to traverse known distances. At high energy, differences are small and require excellent resolution. Time separates identities. Duration classifies matter. In space-based particle detectors, timing helps reject background noise by identifying coincident events. Real signals arrive together, random noise does not. Time correlates truth. Simultaneity filters reality. Neutrino experiments rely on precise timing to associate rare detections with distant astrophysical events. Correlating arrival times across observatories strengthens confidence. Time connects weak signals. Agreement confirms origin. In gravitational wave astronomy, timing accuracy across detectors allows triangulation of sources. Differences of milliseconds can map sky position. Time draws directions. Arrival order tells location. Laser phase noise influences timing precision in interferometric measurements. Stabilizing lasers improves time resolution. Light must be disciplined to measure time. Order emerges from coherence. Clock comparisons in space test whether time dilation behaves identically for different clock technologies. Agreement supports universality. Time treats clocks equally. Mechanism does not matter. Quantum projection noise sets a fundamental limit on measurement precision. Averaging over many particles reduces this noise. Time smooths randomness. Quantity calms uncertainty. Advanced clocks operate near quantum limits, where measurement itself perturbs the system. Balancing observation and disturbance becomes essential. Time is delicate at its edge. Keir replaces force. In some experiments, clocks are deliberately placed in varying gravitational potentials to amplify relativistic effects. Elevation becomes a tuning parameter. Time is adjusted by placement. Geography shapes duration. Orbiting clocks experience periodic relativistic modulation as altitude and speed change. Analyzing this pattern confirms theoretical predictions. Time oscillates gently. Motion writes rhythm. Relativistic corrections are included in software pipelines that process timing data. Automated systems handle complexity quietly. Time flows through code. Algorithms guard accuracy. In long-duration missions, COT performance is tracked over years. Trends reveal aging and environmental influence. Time observes itself over time. Longevity teaches behavior. Timing errors often reveal themselves as systematic drifts rather than sudden faults. Detecting them requires careful statistical analysis. Slow change demands patience. Time hides in trends. Timekeeping is deeply tied to reference frames. Choosing the wrong frame introduces apparent anomalies. Correct perspective restores order. Time depends on the viewpoint. In relativistic experiments, synchronizing clocks in different frames requires careful protocol. Assumptions must be explicit. Agreement depends on convention as well as physics. Time needs rules. Spacecraft navigation teams routinely transform times between multiple scales. Each transformation preserves meaning while changing context. Time is translated, not altered. Interpretation matters. Precision timing also underlies data compression and transmission scheduling. Knowing exactly when data is produced helps manage limited bandwidth. Time organizes information. Order saves resources. In planetary science, timing of occultations reveals atmospheric layers and ring structures. Precise ingress and egress times encode geometry. Time outlines shape. Moments sketch worlds. Even tiny moons can be characterized through timing variations in orbital motion. Gravitational interactions leave temporal signatures. Time traces mass. Delay reveals influence. Across all these domains, timing experiments succeed because they respect slowness. Effects accumulate quietly and reveal themselves only through steady observation. Time favors calm attention. Measurement becomes listening. Time in space is often revealed not through dramatic changes, but through long stretches of consistency. A clock ticking steadily in orbit teaches as much as one showing dramatic relativistic shifts. Stability itself becomes information. Calm regularity is a kind of signal. The vast distances of space make time feel expansive, because signals take so long to cross them. A simple message can take minutes, hours, or longer to arrive. This delay encourages patience and foresight. Space gently slows expectations. When astronomers observe distant stars, they are seeing light that has traveled for years, centuries, or millennia. Each observation is a preserved moment from another era. The sky is layered with past times. Looking outward becomes looking backward. In this way, the universe offers a natural archive of time, stored in traveling light. No effort is required to keep it. Motion preserves it. Time moves forward while carrying history with it. Memory is built into space. Cosmic expansion stretches light and time together, linking the age of the universe to the colors we see. Redshift becomes a marker of duration as much as distance. Time leaves its mark on wavelength. Color remembers age. Large-scale cosmic structures evolve slowly, over billions of years, reminding us that some processes unfold far beyond human timescales. Galaxies rotate, collide, and change at a pace that feels almost still. Time flows gently at the largest scales. Slowness defines grandeur. Even so, the laws governing time remain consistent from the smallest particles to the largest structures. The same principles apply everywhere, without hurry or favoritism. Uniformity brings comfort. The universe keeps time evenly. In space, there is no universal clock that all observers share. Each location and motion carries its own rhythm. This plurality does not create chaos, it creates harmony through rules. Many times coexist peacefully. Proper time gives each traveler a personal timeline, shaped by motion and gravity. No two journeys are exactly alike. Experience becomes path-dependent. Time personalizes motion. The spacecraft drifting far from Earth, time is often measured in mission days or years, counted steadily without regard for calendars or seasons. This simplicity suits the quiet of space. Elapsed time becomes the only marker that matters. Continuity replaces ceremony. Astronauts in orbit experience a slightly different accumulation of time than those on the ground, yet daily life continues smoothly. The difference does not disrupt experience. Relativity fits gently into routine. Time adjusts without disturbance. On planetary surfaces, local days and nights define time in ways familiar and unfamiliar. A Martian sol stretches a little longer than an Earth day, subtly reshaping schedules. Time adapts to place. Habit follows rotation. Space missions often adopt local time systems to match their environment, showing flexibility in how time is defined. These choices make operations feel natural despite distance. Time is tailored for usefulness. Practicality guides convention. In deep space, where sunlight weakens and communication slows, time becomes a planning tool rather than an immediate reference. Actions are scheduled far in advance. Anticipation replaces reaction. Time encourages trust. Long-duration missions teach that time does not rush, even when events are rare. Weeks may pass quietly, punctuated by brief moments of activity. Stillness becomes normal. Silence carries duration. The steady ticking of a spacecraft clock provides reassurance that systems remain alive and ordered. Each tick confirms continuity. Time becomes a heartbeat. Regularity comforts distance. In astronomy, Long observation campaigns build understanding gradually. Data collected over years reveals patterns invisible in short spans. Time patiently uncovers structure. Persistence yields clarity. Variability studies rely on timing to understand change, yet the background of constancy is equally important. Knowing what does not change gives meaning to what does. Time frame variation. Stability anchors motion. Even dramatic cosmic events, like supernova, are understood through careful timing of light curves and spectra. Their brilliance unfolds over measured intervals. Explosions still obey time. Violence has duration. In the quiet aftermath of such events, remnants expand slowly, fading over centuries. Time smooths extremes. Calm follows intensity. The universe rests after action. Clocks in space do not feel the ticking they record, they simply persist. Their neutrality mirrors the impartiality of physical law. Timekeeping is indifferent, steady, and fair. Measurement carries no emotion. Human interpretations of time often carry urgency, but space teaches a different lesson. Processes unfold when conditions allow, not when impatience demands. Time resists haste. Space encourages acceptance. The relativity of simultaneity reminds us that shared moments depend on perspective. What feels now here may differ elsewhere. This does not divide reality, it enriches it. Many presents coexist. Cosmic horizons limit what can ever be observed, defining boundaries in time as well as space. Some events remain forever beyond reach. Limits bring shape. Not everything must be seen. Within those limits, the observable universe continues to offer a steady flow of information. Light arrives faithfully, carrying stories from afar. Time delivers messages reliably. Distance does not break connection. Clocks aboard satellites and probes quietly accumulate time without awareness of their significance. Yet their records allow humans to reconstruct journeys with precision. Time remembers us. Instruments hold memory. When missions end, their clocks stop, but the time they measure remains embedded in data. Past moments continue to inform future understanding. Time leaves traces. Knowledge outlives motion. In physics, time is often treated mathematically, yet its effects are experienced gently. Equations describe it, but experience feels it as continuity. Abstraction and sensation meet calmly. Space reminds us that time does not need to hurry. The universe has unfolded for billions of years and will continue far beyond immediate concern. Duration brings perspective. Calm comes from scale. Observing time in space can soften the sense of urgency often felt on Earth. Processes unfold when ready, guided by law rather than desire. Time flows without pressure. Order replaces rush. In this view, time is neither enemy nor resource to be spent, but a dimension through which existence unfolds. It carries events without judgment. Time supports being. Continuity holds everything. The gentle predictability of celestial motion shows that time can be trusted. Orbits repeat, pulses return, cycles continue. Reliability soothes. Regularity reassures. Even where relativity reshapes duration, the reshaping is lawful and smooth. There are no sudden tears in time, only gradual differences. Time bends softly. Consistency remains. As attention rests on these ideas, time itself feels less urgent and more spacious. Understanding replaces anxiety. The universe keeps time quietly, and so can we.